Just going to finish off our first section of complex numbers with looking at polynomials in general and complex numbers. And this is a key thing. So if you've got a polynomial, all the coefficients are real, then your solutions will appear in conjugate pairs. So you'll always have an even number. Every polynomial can be factorised down to be a mixture of quadratic and linear factors. Now, if you go over the complex numbers though, it now means we can have n linear factors. Everything can be broken down to be linear. Okay, we're dealing with complex numbers, but we can get a linear factor. What that basically means is if you've got an odd-ordered polynomial, so a cubic, a pentic, something like that, it must have a real solution because those complex ones are appearing in pairs. Start with a very basic one. Here's a quadratic. X squared plus 2x plus 2, which now we could do by completing the square. So x plus 1 squared plus 1, and there it is factorised. X plus 1 plus I, x plus 1 minus I. Quartic. This quartic looks like a quadratic, so we can solve it like one. So we get x squared minus 3, x squared plus 4. Well, over the real numbers, x squared minus 3 is the difference of two squares. Okay, I've got to use a surd, but I can do it. X plus root 3, x minus root 3. So that would be factorised over the real numbers. We can now take it a step further and factorise it over the complex numbers. Because x squared plus 4 would be x plus 2i, x minus 2i. And of course we have to solve it. Well, if we're using complex numbers and we've got 4 solutions, real numbers we'd only have 2 solutions. So our factor theorem was that if x minus a is a factor, then we know we can substitute a into the polynomial, it'll be 0. And if it was ax minus b, then we'd sub in b over a. So let's factorise this cubic. But the key here is it's a cubic. It's a cubic, so we know it's got a real solution. It's a logical one to try, isn't it? Minus a half. I mean, I'm sure that would be your first guess as well. Remember, we know it has to go into 5, but it's not monic, so we could have divided by 2 as well. So minus a half happened to work. So all right, I know 2x plus 1 is a factor. I can do a polynomial division, or however I do it, get the other factor as x squared minus 2x plus 5. And of course now I can factorise x squared minus 2x plus 5, completing the square on that. So we'll have x minus 1 minus 2i, x minus 1 plus 2i. All right, we've got a quartic. It has 2 rational zeros. Find them and then factorise over the complex field. Fortunately, the constant's prime, so 3 and 1, that narrows it down. But it's not monic, so I could have over 4 as well. So yeah, let's try a half. Oh, look, it works. Excellent. So a half happens to be 1. So I know 2x minus 1's a factor. Well, let's work out the other factor. Leading term times leading term gives me the leading term. Constant times constant. Now let's work out these missing bits. It'll be 5x if I'm looking at how many x's do we have. Ends up being 5x. Now if I try the x squareds, we want 5x squared. At this stage I've got, what have I got? I've got 10x squared at this stage, haven't I? Therefore, that must be plus 5x squared in there. You can do it that way, do it by division, however you do it. There's the other factor. Now let's try and identify the other rational factor. It's got to be a factor of this cubic now. What shall we try? Yeah, minus 3 on 2 seems to be a logical one. Oh yes, look, 0. Yeah, gee, we're getting lucky today. Now, therefore, we know 2x plus 3 is a factor. We know the 2 rational zeros. That was the first part of the question. So a half and minus 3 on 2. Now we've got to factorise the whole thing. But we know 2x minus 1, 2x plus 3 are 2 factors. That means the leading term must be x squared in the other one. The constant must be 1. Just got to work out how many x's go in there. All right, well, we know we should end up with 1x. At this stage, what have we got? Ooh, gee, hang on. I've got 1 times 3 times 2x, that's 6x. I've also got 1 times 2x times minus 1 minus 2x. So I've got 4x. I need to get rid of another 3x. So 1 times 3 times what would be negative 3x. That'd just be x. Excellent. Excellent. X squared plus x plus 1. Now let's factorise that. Completing the square, we get x plus a half squared plus 3/4. There it is, factorised. Now, it is really tempting to get rid of these fractions. Be careful if you do that, because if I get rid of them, these will become 2x. And then when you expand the whole thing out, you're not going to have 4x to the power of 4. You'd end up with 16x to the power of 4. You'd need to put a quarter out the front as well if you wanted to do that. So it's probably easier just to leave it as fractions in this one. This time we know it has a real solution, but it's a double root. Multiplicity 2. 45. Well, at least it's monic. 45, we could have 1, 3, 5, 9, 15 or 45 and negatives of those. Polynomial z. Let's see what works. I differentiated. Then I tried 1 into that. It didn't work. So I know that's not the double root. I tried 3. It works. It does not mean that's the double root, but it means it's a possibility. Now sub it into there. Ah, yes, it is the double root because it works for the polynomial as well. So I know z minus 3 squared is a factor. Okay, let's work out the other bit. Leading term times leading term. So that's going to be z squared. Constant times constant. So I've got minus 3 squared, which would be positive 9. Positive 9 times 5 is 45. How many z's? I want minus 30. At this stage, I've got minus 6z times 5. What's that? Minus 30. Oh, that's what I want. Excellent. So there's no more z's in the second one. And to do it over the complex numbers, difference of 2 squares, z minus root 5i, z plus root 5i, there's our solutions. Now, I suppose I didn't need that second last line, because it just said solve it. It didn't say, factorize it. And I could have got that from z squared plus 5 equals 0 anyway. All right, let's play with polynomials.